Computers overtook the world by storm in the 1980s. Every home, school, and office wanted to have one because computers make life easier. Today, it is no different. Computers are used for everything, and we're constantly surrounded by mini-computers like smartwatches, phones, and laptops. But have you ever looked beyond the shimmering screen of millions of color crystals and wondered how they could do so many cool things? Of course, you may have heard of computers working with ones and zeros, but why those two numbers? And why 2 instead of our standard system of 10? So prepare for a dive into the sea of zeros and ones and discover why they are a key component of all the fantastic things computers do daily. In everyday life, we use the base 10 system. This system, along with any other number system, is a positional one. This means that the place of each digit conveys its weight in a number. We use digits from 0 to 9, and we can represent any number we want. For example, the number 158 is defined by 1 times 100, or 10 to the power of 2 because 1 is in the third place. The next digit is 5 times 10, or 10 to the power of 1 because it is in the second place. Finally, we have 8 times 1, or 10 to the power of 0. This system works great for calculations and representing numbers. Still, a 10-base system would be challenging to use for processing data on computers. That is why we use a more straightforward system, a binary system. It works the same way as the decimal system, except it has 2 possible values instead of 10 for each placeholder of a number. For example, we would approach number 00110101 in the following way. Each digit in this number has a placeholder value. The first one has a value of 1, or 2 to the power of 0. The following 0 is 2 to the power of 1, or 2. The next value is 2 to the power of 2, which is 4. Next is 2 to the power of 3, which is 8. After that is 2 to the power of 4, which is 16. Then we have 2 to the power of 5, so that's 32. Then there is 2 to the power of 6, which is 64. And finally, we have 2 to the power of 7, which is 128. So our number in decimal value would be all the placeholders with the numeral 1 added together. 1 plus 4 plus 16 plus 32 is equal to 53. We can represent any number using binary, depending on how many bits we have. A bit is a single digit in a binary number. Old computers used 8 bits, limiting processing to only 255 numbers. Why 255? An 8-bit processor is like 8 boxes lined up next to each other, and each can be filled with a 0 or 1. Because the largest number in an 8-bit number is 1111111, and its value corresponds to 255. The more boxes we have, the more numbers we can write, and the computer processing becomes better. Modern computers use 32-bit, or most commonly 64-bit processing units. This ups our number supply to 18 quintillion 446 quadrillion 744 trillion 73 billion 709 million 551,615. However, computers could also represent negative numbers by reading the first digit from the left. If the digit is 0, the number is negative, and if 1, the number is positive. So in reality, we have numbers from negative in 9 quintillion 223 quadrillion 372 trillion 36 billion 854 million 775,808 to 9 quintillion 223 quadrillion 372 trillion 36 billion 854 million 775,807. How do computers use these binary numbers? Binary numbers are processed using logical circuits when put together can make adders, subtractors, and so on. All of these circuits are in the central processing unit, or CPU, and here is where the magic of a computer happens. But how does the CPU know the difference between 1 and 0? Inside the CPU, there are many things called transistors. These tiny objects are designed to control the amount of electricity passing through. Low voltage represents 0, and high voltage represents 1. Suppose we wanted to express our decimal system. In that case, a transistor should be able to distinguish 10 different states, making processing much harder and harder to store things on the computer. This is the core reason why we use binary. It is simple, elegant, easy to store and process, and stable for usage. Binary is used in every computer today, and it will most likely continue. Computers with 3 states, and quantum computers that can be in 2 states simultaneously, have been invented. However, they're not stable enough for usage like binary computers. So for now, the code that enables us to enjoy computers today is made of a sea of just ones and zeros.